Hello, so in today's lesson we're going to be learning about functions. So our learning targets are, I know the definition of a function, I understand the three basic representations of functions, and I can evaluate functions for inputs in their domain. So first things first, let's go over the definition of a function. So a function is a relation in which each input is paired with exactly one output. So pretty much everything that we do with functions is tied back to this definition that a function is a relation in which each input is paired with exactly one output. So one way that I like to think of functions personally is like a machine. So here's our function machine. We have a crank. We have our input goes in here, and our output is here. So essentially we put something into the function. So if we put in a 7, then the machine does something to that number, and out we could get, say, -5. We could put in 10. We put 10 into the input. The function machine does something, and out we get 2, for example. And you notice each of the inputs is only getting one output. We could put in red, and we get out green. So a function doesn't necessarily, there's nothing in this definition about numbers, so a function could include anything as its input as long as each input is paired with exactly one output. So I think the machine is a good way of kind of thinking about functions as a general entity, but for math class we're going to want to be a little bit more specific with how we're representing our functions. So before we do that, just some vocab. Is all of our inputs collectively for a function are called our domain, and all of our outputs are collectively called our range. So that's just some vocabulary for you guys to get down. So the three representations of functions are tables. So a table of values could look like this. We could have that's an example of a table of value of functions. We could also have a function that looks like this. So those are examples of functions represented as tables. So our x values would be our inputs, which are also collectively make up our domain, and our y value would be our outputs, which collectively would be our range. Same thing here, our day would be our input, and our color would be our output. So for something like a school spirit week, we could make a function based on what color you're supposed to wear on a certain day. So on Monday you're supposed to wear orange clothes, on Tuesday our output is green clothes, on Wednesday our output is yellow clothes. So hopefully you can see that a function doesn't necessarily need to have numbers. So Representation number 2 would be a graph. So on a graph of a function could look like this. Or could look like this, for example. Or we could have an equation. So an equation would be like f of x is equal to 5x plus 3. You could have f of x is equal to x squared minus 8, for example. So those are our 3 representations. So, for the rest of this lesson, we're going to look a little bit more in detail at each of those representations and how we can deal with them. So, we're going to open up a new window. And first, let's go over tables of values. So, suppose we want to determine whether or not a table of values represents a function. So, our first question is, does this look like a function? So we're going to use inspection, inspect each of our inputs and each of our output, and see if they represent a function. So what we want to check for is to see that each x value is paired with exactly one y value. So negative 2 goes to 5, negative 1 goes to 18, 0 goes to negative 77, negative 1 goes to 65. Now wait a second. Notice that negative 1 goes to both 18 and 65. So this means that this is not a function. If we go back to our machine analogy, if we put in a negative 1, we could get either an 18 or a 65, which that is no good. So we could say that our machine is malfunctioning because it's not a function. So that's my bad joke for the day. I want to look at one other example where, suppose we have so here we see negative 3 goes to 5, negative 2 goes to 0, negative 1 goes to negative 5, 0 goes to negative 14, 1 goes to negative 5, and wait a second. So both negative 1 and 1 go to negative 5. So even though this might look a little bit strange at first, this is a function. It is okay for different elements of the domain, different inputs, to give us the same output. So it's okay if in our machine we put in a negative 1, and we get a negative 5, and we put in a positive 1, and we also get a negative 5. That is okay. So we just want to make sure, once again, look back at our definition and make sure that each input is paired with exactly one output. So that's kind of table of values. So for graphs, we have something called the vertical line test. And so what the vertical line test tells us is that if we want to find out whether or not a graph is a function, what we want to do is we want to draw vertical lines through our graph at every point. And if our vertical line passes through 2 or more points of the graph, then it is not a function. So if we look at this one, no matter how many vertical lines we draw, it's only going to pass through one point. So this one is a function. Whereas suppose we have something that looks like this. So far we're good. So far we're good. But wait a second. You see this vertical line passed through 3 different points. So this one is not a function. And so the vertical line test is really just a way of applying our definition of a function, because our inputs are our x-axis and our outputs are on our y-axis. So for each input, so if we have an input of 1, say, on this function, our output is -5. So you see for the input of 1, we only get 1 output. And we can test that for any input, which would be our x values. But here, suppose this input is -1. You notice for our input of -1, we're getting an output of 2, -2, and -3, which is obviously not a function. So that is our vertical line test. And finally, equations. So for equations, I want to go over what's called function notation. So function notation is written like f of x is equal to 3x minus 8. So f of x itself is our output. And x is our input. So a common mistake that people will make at first is they think that on the left side of the equation we have f being multiplied by x or something. But that's not how it works. We call this f of x. And f of x is its own entity. It's the same as saying we have y is equal to 3x minus 8. The only difference is that f of x allows us to clearly mark what our input is. So say for this function, we have f of 2, that's going to be equal to 3 times 2 minus 8, which is equal to 6 minus 8, which is equal to -2. So again, we're able to clearly mark what our input is and what our output is. We have f of -5, it's going to be equal to 3 times -5 minus 8, so -15 minus 8, which is equal to -23. So that's an example of a function in equation form. Let's do one more. Let's do f of x is equal to 2x squared minus 5. So if you look at what f of 3 is, it's going to be 2 times 3 squared minus 5. 3 squared is equal to 9. So 2 times 9 minus 5. That's equal to 18 minus 5, which is equal to 13. And then say we have f of -2. This time -2 is our input that we're plugging in for x. It's going to be equal to 2 times -2 squared minus 5. -2 squared is equal to -2 times -2, which is equal to +4. We get 2 times 4, that's equal to 8 minus 5, which is equal to 3. So our input is -2, our output is 3, and here our input is 3, our output is 13. So that concludes our lesson on functions. So in our next lesson, we're going to use these tools that we built up in this lesson and apply them to all sorts of different linear functions. So stay tuned for that.